If you can hear me, go down to the bottom of your screen where the little guy is with the green check mark on him. Click on that and then click on the agree button. Basically, you're giving me a green circle. Okay, we're short on some people tonight as far as getting started. So I'm going to do a little bit of material before we start talking about the mechanics of the class, because I don't want to have to go over that twice. So let me see. Make sure you keep your microphone turned off, but I do need one of you to talk to me for a second here. Peter, are you there?
Can you hear me?
Yeah, okay, I can hear you. I wanted to make sure. I had a problem last night. I was working in a different lab or yesterday afternoon when I was teaching, and all of a sudden everything just disappeared. So I can hear you just fine. Okay, so let's get started. And like I say, we'll come back and talk about procedural stuff a bit into the class, but we need to have more people here. We're missing 2 or 3 people still. Okay, so let's assume for a second that we have been given a binary number. So let me grab a thing here for a second. And so we get a number that looks like this. Well, and one of the questions that comes up to us very often when we're working in computer architecture is, based on the value of that binary number we have, how many possible binary numbers are there that will fit in that same amount of space? Because that has relatively very much to do with the storage of information. If we take ourselves and we just take a single bit of data, I'll just put an X there to stand for a single bit, and we assume we're working in binary or base 2, that X can assume 2 values. It can be a 0 or it can be a 1. And that's the only 2 values it can legitimately have mathematically. Now, we know there are some other things that could go on in an implementation. For example, the bit could get lost, or the bit could not be turned on or off. It could be driven by a signal which only allowed it to be halfway on. So all those things exist. But at least for the first part of the course, we're going to assume that our number systems are pure, and that if I give you 1 bit, I can store 2 things, either a 0 or a 1. Now notice that the name of the base is base 2. Very much like if we're operating in base 10, we have the digits from 0 through 1 less than the base name available to us. So if I told you we're working in base 4, you would know we have 0, 1, 2, and 3 available to us. Now, how do I know that this is a binary number? Well, because I told you it was. Not because of the fact it's only 1s and 0s. That's a perfectly good decimal number. That's a perfectly good base 8 number. That's a perfectly good, base 128 number. It just turns out that the instance of the number we were dealing with is in binary or base 2. And that can turn out to be a little bit of a problem, because in order to indicate the base of a number, normally what you do is on the right-hand end, as a subscript, you put the base in decimal. Now, in the editor I'm using right now, I don't have any way to do subscripts. So if I were to write a 2 there indicating it's base 2, that would just be confusing. So what I'm going to mostly tell you is, during this course, it'll be very clear to you which base we're working in at any given point in time, if you're paying attention. I mean, if you don't pay attention, obviously it won't be. We will tend to be working in binary or in hexadecimal, base 16. And very frequently, it'll be very easy to tell whether we're in base 16 or base 2. Sometimes there'll be a question, in which case I may have to give you the base, or I may say the number you're looking at right now is in base 4. But I don't think you'll have as much trouble as it sounds like you could potentially have with that. Now, one of the numbers that is an interesting number to show and tell is, without knowing the base, and I ask you what the value of that number is, you would have to tell me it's the number of the base itself. So the number that looks like 10 in base 2 is going to be the number 2. In base 3, it's going to be the number 3. In base 32, it's going to be the base number, or 32. So let's think for a second about, in our normal operation of something in base 10, this number is in base 10, what those positional positions mean. This really means that we have 2 times 10 squared plus 3 times 10 raised to the first plus 4 times 10 raised to the 0 power. So positionally, we can determine by starting on the right-hand side and calling that base to the 0, base to the first, base squared, base cubed, base to the fourth, and so forth, and then simply sum up, when we're done, the results we would get. So 10 squared in decimal is equal to 100 times 2 means this is equal to the value of 200. This guy now is times 10. 3 times 10 would be a 30. And 4 times 10 to the first, or any base to the 0 power, any base to the 0 power is going to be equal to 1. So 1 times 4 is a 4. So we would add those up and we get 234, which is what we already knew because we tend to speak decimal. That's what we're used to doing. So if we're operating in another base, the same things will be true. If I went to my original number up here, the number on the right-hand end is equal to 2 to the 0 power. This is 2 to the first power. You can tell my keyboard's off by 1. Second power, third power, fourth power, fifth power, sixth power, finally the 7th power. These numbers, of course, are in decimal. This number we're assuming at the moment to be in binary. So we would take 1 times 2 raised to the 0 power. Since all of these numbers here are going to yield a 0 anyway, we don't have to worry about those. The next one we have to worry about is this guy times 2 raised to the 5th. 2 to the 5th is 32. Times 2 to the 6th, we add that in, 2 to the 6th is 64. So knowing our powers of 2 is going to be one of the things that we need to make sure we do very early on in the semester. We don't allow ourselves to forget them. So they're actually fairly easy to do if we start and we know we have 2 raised to the 0. If I can find that key again. Where's that key? There it is. We have 2 raised to the first. We have 2 raised to the second. We have 2 raised to the third. We know the guy on the right is always equal to 1. So 2 to the 0, anything to the 0, at least in the world we're working in right now, is equal to a 1. This guy is going to be equal to the base himself. This guy is going to be double that, or a 4. We're working in decimal now. Double a 4, you get an 8. So 2 raised to the 4th would be a 16. And on the website page, if we go there, the URL of this so that you can find it again is H. If you go to that URL, let me scroll it to the top here if I can. You should get a page, and the page, let's see if I can get it to refresh here. Should look like this. You might have to refresh your screen like I did. But one of the items in the list is an entry called powers of 2. So if we click on that, I'll zoom in a bit. We can see 2 to the 0 is a 1, 2 to the 1st is a 2, 2 squared is a 4, 2 to the cubed is an 8, 4th, 16, 5th is 32, 64, 128, 256, 512. What I need you to do, and this is a homework assignment, I need you to memorize your powers of 2 from the 0th power to the 16th power, which is 65, 536. So you need to, if I ask you in the next class, if I call on you and I say, what's 2 to the 10th, you should just automatically say 1024. If I say, what's 2 to the 15th, you should say 32,768. So mark that down as an important thing to remember. Don't come to class and not have that memorized, because we're also going to take them into negative exponents and things like that very quickly. Well, what that says is, back here was this original number we had. We're going to be summing up 2 raised to the 1st, I'm sorry, the 0th, and 2 to the 5th and 2 to the 6th. So once we memorize these, they become very easy to do. But 2 to the 0 is going to be a 1. 2 to the 5th is going to be a 32. 2 to the 6th is going to be a 64. We're adding those up. We see that the number we have at the top is a decimal 97, if I did the arithmetic correctly. Now that's going to come in handy, because if we needed to convert numbers, for example, let's say somebody asked us to write down the number. Let's take something easy. 67, that's a decimal number. Okay, that's in decimal. What is it in binary? So work that out. See if you can get an answer for that. Okay, so an easy way to do that is to look and see what the nearest number is to it, hopefully underneath it in this case. So 2 to the 6th is a 64. So if that's the 6th position, nothing at 5, 4, 3, 2, 1, or 0. And we see this number is 3 more than 64. So 3 more in terms of powers of 2 would be a 2 and a 1. They added together give you a 3. So we would know that these two guys right here, the one that's equal to 1 and the one that's equal to 2, would be available to us. So we've got the 1-bit, the 2-bit, and the 64-bit turned on. 64 plus 2 is 66 plus 1 is 67. So he would have done a conversion into the decimal number of 67. Now, if we have 4 binary digits in a row, we call that a nibble, sometimes spelled like this. 1 bit all by itself is called a bit. 8 bits is called a byte. 16 bits is often called a word. And we'll learn when they're called that, when they're not. But in general, we should be able to look at a bit, see it's 1 or 0, make a determination about something. Same thing with a nibble, which is half of a byte. That's why it's called a nibble. We should be able to look at those 4 digits, and we should be able to determine what its value is fairly easily. Now, let me show you some nibbles. I just happen to have some written out here on another screen. So, if none of the bits are turned on in the nibble, the value of that is 0. If only the bit which is 2 to the 0 is on, it's a 1. If only the 2 to the first is on, obviously it's going to be a 2. If both of those are on, it's a 3. If only the 2 squared bit is on, we have a 4. 4 plus 1 is 5. 4 plus 2 is 6. 4 plus 2 plus 1 is a 7. Only the 8-bit is on. 8 and 1 is 9. 8 and 2 is 10. 8 and 2 and 1, so 8 and 3 is 11. 8 and 4 is 12. 8, 4, and 1 is a 13. 8, 4, and 2 is a 14. 4 ones would be an 8 plus a 4 plus a 2 plus a 1, which is a 15. Now, what's the interesting fact here to know and tell is that if you have 4 bits, you can only put 16 different things in them. So 2 raised to the number of bits you have, 2 raised to the 4th is equal to 16. I was able to put 16 different things in there, 16 different variations of 1s and 0s. I can't put any other variations because there aren't any other variations that fit in 4 bits. James, I see you have your hand up. Do you have a question?
Sorry, can you hear me?
Yep.
How much is a byte in a word again?
You'll have to check your notes on that. I can't teach the class twice.
All right.
Okay, so now when we have 16 places, we can put 2 to the 4th number of things in it. You could ask yourself, well, if I had 6 bits of data, how many possible combinations of 1s and 0s are there? And you would answer that 2 to the 6th. And when you are finished memorizing these, 2 to the 6th, of course, is 64. So what that says is that no matter how hard I try, if I have 6 bits of data, I can't store more than 64 unique things in it. That's not much information normally, but perhaps my problem doesn't require more than 64 unique things. But keep that formula kind of in mind, that 2 raised to some power, which is the number of bits you have, will tell you basically how many combinations of 1s and 0s you can stuff into that number of bits. Now, normally this would be inconvenient. If we wanted to write some nibbles and then write their values next to them, some of these numbers become 2 digits. And what we really would like is to have all of the numbers be single digit. Because if we did, then we'd be able to take the nibble and treat it as though each of these digits were a base 16 number or a hexadecimal value. So what we do is when we get to 10, instead of continuing with 2 digits, we simply label this with an A, a B, a C, D, an E, and an F. So now we have a single digit which can hold down the position of one of these variants of 16 places. So a nibble represents a single digit in base 16. 16, of course, is written in decimal. Bases are always written in the decimal system. We would normally speak these with a mnemonic type of name, like, or phonetic. Like you might say alpha. You might say Bravo or Baker. You might say Charlie. You might say Delta. You might say Echo or Easy. You might say Fox or Foxtrot in order to do that. So if somebody gave you a number like this, and they ask you what number you had just written down, you would say 3 Delta Foxtrot. And they would understand immediately, oh, yeah, I know what he's doing. Notice I didn't write base 16 because it's clear this can't be 2 or 10 because it's got letters in it that can't be in those bases at all. Could be something else, but the 3 we're really working with right now are base 2, base 10, and base 16. Now you in fact need to memorize these patterns, what their value is, and both of their names down here. So if I ask you to take this number right here and turn it into decimal, you'd say 11. If I said take this number and turn it into base 16, you'd say Bravo. That way, if we have a number like this, we can divide it into 2 halves. Oops, can't do that. I think the number was up at the top. Well, I've erased it already, but if we had a number like this, we could break it into 2 nibbles. We see this is a 9, this is a Charlie. Or in decimal, this is a 12, this is a 9. Now, since these are basically the same thing as hexadecimal digits, if I write them down as hex digits, 9, Charlie, whoops, somebody went to sleep there. I would know that this is C, or 12 times 16 to the 0. This is 9 times 16 to the 1st. Now, I can't do 9 times 16 in my head. So what we normally do in this class is we get our grocery store calculator. Now, a grocery store calculator is one that doesn't have all sorts of features. Something that's really simple and dumb like this one. No signs, no cosines, no solve big complicated problems. The biggest thing this has on it is a percent sign. So what I could do is I could say, okay, I have 9 times 16 plus 12. 9 times 16 plus 12. And that means that number right here is equal to 156 in decimal, assuming I hit the right keys on the calculator. I would always check myself. I also know that this is also 2 squared plus 2 cubed plus 2 to the 4th plus 2 to the 7th. We add those up, we'll get 156. Now, if this number right here represents a decimal number, I know in writing it out in nibbles, it's 1, 2, 3, 4, 2, 3, 4. So it's a 1, 0, or 1 times 16 plus nothing. So 1, 0 in hexadecimal. That means it's worth 16 in decimal. A rule to know and love is that if I make the bit that I had turned on a 0, make all the rest of them 1s, I have the value that's 1 less. And that's true for any number I write. Let's say in binary I write this number right here. I have no idea what it is, not going to bother figuring it out. But what I do know is that that number is 1 less than the first number. Now, we're obviously going to learn how to do mathematics and conversions and all sorts of things with these, but that's the general kind of idea we would have. Let's take a simple one and see if we could figure out how we would go about doing that. Let's say that somebody said what they wanted was the decimal equivalent of the number 61. That's like that, or the hexadecimal and the binary value of that. So this is decimal. Let's turn it into binary. Oh, we look at our list. The nearest thing to it is 64. And 64 would be, this is the 6, this is the 5, 4, 3, 2, 1. And the 0 position, right? So we would have this number. We know this number is too big. But what we also could say is, if that's 64, that's 63. How much bigger than 61 is 63? Well, it's 2 bigger. So that means if I took this same number and got rid of the 2, I'd have the right answer. Of course, to write that in hex, I need to break it into 2 nibbles. And since it's missing a digit on the front right now, we'd have to put that in. We'd get 00111101. And the hexadecimal value of that is a 3 dog. Now, assuming I did the math right, we would be in the ballpark of our answer here. And you go back and check, because I occasionally throw in just a mistaken number when I'm typing on the screen here. You've seen how great I can type. But that's the general idea. We get the number that's closest. If it's less, move the number down to the one that's slightly lower, 1 less, and then take things away rather than adding 2. Normally when we present an answer, unless we're told otherwise, if it's in binary, we'll do it in groups of 4. So we'll basically do nibbles. So we're going to memorize our powers of 2 from 0 through 2 to the 16th. Now, I gave you more than you need down here. I mean, if somebody ever came up in a trivia question and said, what's 2 to the 256th? Well, I can't even get it all on the screen at once. I'm sure you'd be ready to spout that number out. So I found it rather pointless for you to memorize that because we can always look it up if we need it. But the other ones, we use them so frequently that you'll want to have them right at the tip of your tongue. Additionally, you need to have this table memorized, the nibble table. If I say 1000, your head just immediately goes 8. If I say 1011, you go 11, and in thinking in hexadecimal at the same time, you go B. Remember, these numbers in decimal and hexadecimal are equivalent. It's not that we get to 10 and have to reduce it to a single digit that we see a difference. But you do have to know these. So, again, if I were to ask you in the next class, what that value is, in your head, you divide it into 2 parts. Make sure they both have 4 bits. If they need leading zeros, put them on there. We see this as 1111, which is an F, or 15 times 16. And we see this guy here has the 4-bit and the 1-bit turned on, so he's a 5. So you'd answer me with an F5. Then we could, of course, do 15 times 16. Is equal to that. Plus, we could add to it the 5. And we'd see that this number is equal to 245. Okay, does anybody have any questions at this point? Okay, well, I believe we've got a quorum right now. It looks like everybody's here, at least number-wise, that's supposed to be. So let's talk for a second about the syllabus, which I have stockpiled away somewhere here. Whoa, that's big. Okay, let's go over the great details of the class. This is Fundamentals of Computer Architecture and Assembly Language. We do both. My name is there as well as my email. If you're going to email me, a couple things are important. One of the things that's important is that I don't get my email regularly. Somebody else actually does my email, and then they pass on to me the things that I need to do immediate attention. And those are usually business problems and things as opposed to schoolwork or any of the other things that I do. So if you write me an email and don't get an immediate response, it's probably I haven't seen it yet. I know I have a couple from this class they said that I haven't even been given yet. We will work out a way that we can use office hours to communicate as necessary. If you're going to send me an email, though, and you will when we take a test or do something like that because we turn things into text files and mail them, use my email address here that's in the syllabus, and make sure you include in your subject the name of the course, COS231. Additionally to that, make sure you use your Mercer email. You don't send me something from, Big Dog at canyon.edu or something. Make sure it's from Mercer College. More chance of getting to look at it that way. Coming into the class, you should have all the information that 102 would give you in terms of using your computer. I'm not going to teach you how to use your computer in here. When I ask you to use the console, I expect you to know how. If you don't know how, you need to either work with other students in the class to figure out how in advance, or you need to get tutoring. It's not something that I'm going to have time to spend with you, teaching you how to use your computer. 102 should have taught you that, and 101 if you didn't have the prereqs to start with. Now, when you are using your computer, all of the examples I use in class are going to be on a Windows 10 system. If you're using a Mac and can use a virtual machine, that'd be great. If you can't, then you're going to have to yourself figure out how to modify scripts and things as necessary, because that's part of using your computer. Same thing if you're using Linux. If you're using Linux, you should know what you're doing, or you shouldn't be using Linux. And things like console or adding your path or adding environment variables All those things should be just things you can do. In here, we're going to need Java. You need to check, and we'll actually do an exercise in class where we check to make sure you have the right version, but you'll need to make sure you have version 15 or higher. And currently 16 is the highest one that's out there that's actually usable. There are some other versions, but they're not practical for what we'll be using them for. Now, there is no specific textbook in this class, but there will be a lot of reading you will want to do on topics we cover. I don't lecture during class. What looks like lecture normally will be to solicit participation on your part. I use a kind of question and answer type of thing where generally I'm not going to directly answer your questions. I'm going to give you back a question. And quite often I'm going to call on you at the start of class to parrot back to me things that I ask you to learn or things that you should have read about because I brought them up in class even if I didn't talk in detail. So you want to make sure you're really on your toes with that and that you're really trying to get this class going for yourself. Don't let yourself get behind. I assure you there are many people who have, and many of those people never finished. Or worse, they got a bad grade and never came back to correct it. We are going to, however, require a microcontroller kit. We're going to be using toward the end of the semester the ATmega 328P. Let me write that down for you here. P is capitalized. Microcontroller. It's the same one that is in an Arduino Uno Rev 3 board. Now, you're going to need to buy one of these, and you're going to need to get the USB cable that's appropriate for it in order to attach it to your computer. We'll be using Arduino software in order to be able to let the Mac and Linux users not have to write as many scripts, but we won't be doing anything really Arduino-ish. So if I just search on the internet here, let me grab a window, and I say Arduino Uno, I'm going to see a store. Probably you're getting the same ad I am. If not, you want to go to the location being arduino.cc. And if I just go to the store and say I'm in America, this is an Arduino Uno Rev 3. Now you may have to search their site a little bit to find it. It only costs $23. You want to make sure you get the Rev 3. You want to make sure it's an Uno. You want to make sure it has the large chip right here. There's some that have a little tiny chip here. They're not appropriate. Secondarily, although you can't really tell, but if you get an Arduino that's really an Arduino, you'll find out, there's a second Arduino chip here that handles the USB. Some of the bootleg type designs have a different chip here and things don't work as smoothly. The other good thing about this is in a socket, so if you happen to burn it up for whatever reason, you could replace it. Now, if you get this, you also want to get the USB cable down here. It's a type AB cable. You would check that. The total price goes up to something, I don't see the price anymore, but it's bigger than $23 once you do that. Now, another place you can get an equally good one is on Amazon. You type Amazon ELLEGOO, Elegoo Uno. And if we go to the Elegoo site, we scroll around, we'll find right here the Elegoo Uno Rev 3 ATmega 328P with the cable. for $13.99. So it's slightly cheaper and you get the cable. I personally have used about 10 of these in different things, and they work, for me, they've worked perfectly. Will they work perfectly for you? Who knows? It's not a real Arduino. Of course, a real Arduino might not work either. But this has been proven by lots of students as well to be a very reliable board. So you want to buy one of those two, either the one here or the one on the Arduino site itself. And you want to make sure you have the USB cable that goes along with it. We don't need it immediately, but we would if we were meeting face-to-face, because there's some things we would actually be building in class during the class session. We unfortunately can't do that because we can't get together in person. But when we get to this stuff, we'll be able to do the programming and things directly on this board. So those are the two places you want to go. To find this one, I searched for Amazon Elegoo Uno. Let me write that down somewhere. Amazon Elegoo Uno. And then I just searched in their site until I found it. And then the other place I searched for was I searched Arduino Uno. And then I ultimately wound up at the site. And the site you're looking for ends, let me see if I can just copy that real quickly. Right there it is. So it's something, the important thing is to know you're not getting some strange place. Is it ends.arduino.cc. Okay, anybody have any question about what you have to buy? And of course, check with somebody else in the class if you want, and see if they, have any suggestions or anything. I've had extremely good luck with the Elegoo guy on Amazon. You might or might not. It isn't a real Arduino, but it operates almost exactly as one. Well, it operates exactly as one. I saw a hand go up. Who was it? It disappeared afterwards. And unfortunately, with 30 people in the class, I can't see everybody. Robert, was that you? Robert, you have your microphone on. Are you asking a question? Okay, I guess he's not. Everybody, by the way, give me a green circle if you can hear me. The other things I might ask you to do are in that same box or nearby. If you open the little guy up again where the green agree is, there's also a red disagree. Everybody give me a disagree. If for some reason during class you need to get up and go to the bathroom or go to the kitchen for a second and come back, during the short time you're gone, make sure you hit the away tab that's inside that same box we were just in. Also, if I ask you to give me some feedback on something, you can hit the happy, surprised, fast, those type of buttons also if I'm asking for an opinion. Outside of that box, if you go past your microphone, past your camera, there's a little guy with his hand up. Before you turn on your microphone, always raise your hand and make sure I call on you. Now that doesn't count if all of a sudden I disappear or something and you have to tell me about it. But in general, because we have so many people in the class, when you if I say, anybody that can answer this question, put your hand up. I may not call on the first hand. I may call on somebody else to spread the participation around because I want everybody to get the opportunity to participate. That being said, I'm going to go back over to the, where did we put that? Did I get that out of here? There it is. The grades are going to roughly follow this pattern. Because we're not meeting in person, the exams will not count quite as high because it's very easy to cheat on an exam when nobody's looking. Not that anybody in here would, but periodically I do catch people because I do put little landmines in my exams that people tend to trip over a lot and give themselves away. But nevertheless, there'll be more emphasis on these items here. Participation is a big one. You need, and I think I have that at the bottom of the page. If I ask you to participate, for instance, if I call on you just at random, you shouldn't say, huh, what was the question? Like you weren't listening. It shouldn't be, I have no idea what you're talking about, because you should. You should have a reasonable answer available. Attendance means were you here and were you here the entire class time? It's automatically kept for me. And, it doesn't matter if you show up 2 hours early, that doesn't count. When, the ding dong goes off at 6, it starts looking to see if you're in the room. And it looks to see if you're in the room doing, things that you shouldn't have the leave button pushed for. So it knows your computer hasn't, for instance, gone to sleep. So by participating in the class, things like that won't happen. And punctuality, when I start right on time, particularly with exams and things. Don't come in and ask me what the instructions were when you miss them. You just have to guess what they were, I suppose. So participation, attendance, and punctuality. I would assume that anybody in here that can't do those three is going to withdraw. And I suggest it. I don't want anybody to withdraw, but if you can't do those three things, you will not do well in this class. This isn't like my other class where it's a little softer and squishier. This is hard facts. You either know them or you don't. And there's not much I can do about that. I can't just, they thought they kind of got it right. Binary is either 0 or 1. It's not kind of. And so we want to make sure we have that in hand. Now, what are we going to cover? There's a second page here that roughly outlines the units we're going to cover. We'll work on Unit 1 tonight and during the next class a little bit and start Unit 2. Not sure how far we'll get, but Unit 3 will probably be near the next class. So roughly 1 per class, but the first one's got a lot of stuff in it we'll never get to tonight. And again, a reminder at the bottom that punctuality, participation, and attendance are definitely expected, not just desirable, but expected. Anybody have any questions about the course material? Because I'm not going to talk much more about it. Thank you, Manati. That's a good thing to do. Hit the red button if you don't have a question, and that way I know you don't. And of course, if you have a question, your hand should go up. Okay, there'll be more things as the semester moves along that we'll need to talk about that are procedural, but I think it's a little better to do some learning. So let's do a little bit of learning right now. One of the things that we have to deal with is encodings of various sorts. Now, by encoding, I mean, since I have, let's say, 8 bits of data or 7 bits or 6 bits of data, I have to say that means something. Well, we know we can turn it from, a binary number into a hexadecimal equivalent or a decimal value. But sometimes we need these things to stand for things which are not really necessarily numeric. An example of that might be, suppose I wanted to type the word dog. Well, that's not a binary number. The D, I guess, could be considered an ASCII character. Well, I'm not ASCII, I'm sorry, a hexadecimal character. The O could be, can't really be anything in base 16. So what I need to do is I need to take the number of bits I have, and I need to assign those bits to things other than numbers. And then by agreement, we have to say during a certain part of time, I'm working with these not as numbers, but perhaps standing for letters, English language letters. So let's say for a second, what we want to do is we want to learn how to encode ASCII characters. ASCII is one of the older encodings now, but it's still very, very much in use. It stands for the American Standard Code for Information Interchange. We'll probably never ever say that name again. We'll just call it ASCII. By definition, it's a 7-bit code. So we know we have 2 raised to the 7th possible things that can be encoded in it. What is 2 to the 7th? Well, you have it memorized. And you go, well, okay, that's 128. And yes, you're right. There's 128 different things that can be encoded in ASCII. Now, how do we know what they are? Well, we have to go to a table of ASCII codes, which we have on the web page. Let me get that down. Making me really hungry. And we go to the ASCII chart. So from 00 in hex up to 7F, and we think about that, is 7F, what would that be? Well, 7 is 0, 1, 1, 1, and F is 1, 1, 1, 1. That's 1 less than something because all the 1s are on, right? It's 1 less than whatever that number would be. And that number is 1, 2, 4, 8, 16, 32, 64, 128. So the biggest thing in it is 127, which is here. But we also have a 0 in it. We didn't start with 1. So that means we actually did encode 128 different things, just as we promised. Now, we can write out in hex, and then we can turn it to binary if we need to, the word dog. We'd look up a D. We'd find out it was a 44. We'd look up an O. Well, O is lowercase. The O is right here. It's a 6F. And the G is a 6-7 because it's lowercase. But we could write that out in binary, and I'm going to write it out in 8-bit binary, making the first digit a 0 for the moment. 4, 4, 6, F, 6, 7. So there's 1 character here. There's 1 character here. There's 1 character there. So I'll put a little extra space in there so we would know what we're looking at. So binary turns into these hexadecimal digits, and we can use these hexadecimal digits to look things up in the table over here. Now, I'm not going to make you memorize the table, but there are some anchor points that you do need to memorize. The first one is at hex 30, the printable numbers exist. Now, what's the formula for finding one? Well, let's say I wanted the number 5. I'm just going to take a 3 and replace the 0 with a 5. So this is the printable number 5. Printable number 2 would be a 3, 2. Three 0. And 3, 9 would be the printable number 9. Notice that the only number we have to remember is the 3, 0. So that's to be memorized. The 3, 0 is where the numbers are. The second place to memorize is remember the number 40. This is where the uppercase letters live. Now, the first one is not really a letter, but the first letter of the alphabet which is A, is 4 and a 1, right? It's the first letter of the alphabet. That means J, which is the 10th letter, should be at 4A, which is a 10, 4A. There's a J. The alphabet breaks in half between M and N. So this should be a 13. Well, D is a 13, 4D. Notice that we just take the 40 and we add to it the number that the letter is in the alphabet. Now, since we have more than 16 letters in the alphabet, it's going to go past 4F, which is 4 and a 15. So we just carry the 16. So the 16th letter is a P, 17th letter is a Q, 26th letter is a 5A. But the number for you to remember is going to be a 40 plus the letter name. So if I said, what is the ASCII for uppercase? Oh, let's say we wanted to have letter F. You would figure out, even if you have to count on your hand, what letter F is. A, B, C, D, E, F. It's the 6th letter, right? So it's a 4 plus a 6. We go check our chart. That's correct. Now, lowercase is identical, except you need to memorize 60. Where they live. So the same thing instead of 46 would be 66. And again, because there's more than 16 letters, it's going to overflow and we're going to go into the 7s, ending the Z with a 7A, which is 10 plus the 16 we carried, or the 26th letter. Now there's a couple other things in the chart you want to just memorize just as facts. A space is a hex 20. A carriage return is a 0D. A line feed is a 0A. And for the most part, if you know that set, or can navigate your way around quickly without this chart in front of you, you'll be doing fine. Now, when we have a particular thing to send, we really only have 7 pieces of data. I've been writing a 0 in front of it. So let's say we took that 46 that's up there. There's a 4. There's a 6. We could simply, if we were going to send this letter to somebody, stick a 0 in that missing position. If we did, we're doing something called making it space parity. We also could make the character have something called mark parity, in which case, no matter what the letter is, we put a 1 in that first position. Well, so let me leave these next to each other here. So now instead of this being a 4-6, it's a Charlie 6. But the extra 8 here came from it being mark parity, not because it changed the value of the 7 bits which represented the character. There's 3 other common parities. One of them is called no parity, in which case anything can be in that bit. We have odd parity and even parity. What they are is, if I have a number like this, and I'm using odd parity, it counts the number of 1s in that I already have turned on. If that number is an odd number, it puts a 0 at the beginning. If it were an even number, which it's not, but let's say it were this number. It's even and it needs odd parity, it would make the first one be a 1, so that the total number count here is an odd number. Even parity is just the opposite. When it counts the number of bits that it has, so we haven't, let's just write down a random number here. Counts the number of bits, and they're an even number, that means it's already even parity. If it counts the bits, and they're not an even number, but it wants even parity, it will stick a 1 at the beginning of it. And we'll obviously go over many more of those examples, but that's just something you need to have heard before, because when I show you some of the characters and suddenly there's an extra character being turned on, you'll have to resolve what that is. Normally it's a parity bit. Now there is one other option that can occur. Oops, that's not it. When sending, we might also only send 7 bits. And there is no parity, but it's different than this no parity. This no parity simply means that we're going to stick garbage in the first bit. It might be a 1, might be a 0, might always be a 1, might always be a 0, but whatever it is, they're saying don't check it. Now the way parity works when it's even or odd is when you send the data to another station, the people receiving it look to see if the parity bit is correct. If it's not, that means one of the bits might have got changed in transmission, which is a very common thing to happen. And if it is, they know they can't fix it, but they know that they can stop the transmission and have the transmission resent, because it's very primitive error checking. Okay, you might have any questions about that brief discussion of ASCII? Okay, well, in the modern world, it turns out that having 128 characters is not enough, particularly when so many of them are given to control signals. We have a null, a start a header, start a text, into transmission, inquiry, acknowledgement, bell. This, on one of the old computers I used to work on, actually rang a gong when you would send it in 07. Backspace, horizontal tab, line feed, vertical tab, form feed, carriage return, shift out, shift in, all sorts of things, which controlled various devices over the years. But we really don't have that much room for characters. What if we wanted to send a message to a person that spoke German? Well, there are characters in their alphabet which aren't in ours. What if we wanted to do something even more exotic? Like maybe we're working on some Greek literature and we want to put something in the original Greek. Well, we can't do that in ASCII. The way it was done for a while was we made the 8th bit actually index a second 128 characters. And then every country could have its own extra characters. But that meant when I would send something to somebody in Belgium, and they were talking to their Flemish friends, that we couldn't translate, from Flemish to French to English and get things fluently done because those characters didn't exist in the character set, and sending the wrong character is pretty bad. So one of the things that we want to do is talk a little bit about the modern way it's done. No longer do we just simply append a second page. But languages, for example, if we take a language like Java or C++ or even Python, they don't use ASCII for their characters and strings. Java uses something called Unicode 16, which is abbreviated UTF-16. It's a 16-bit representation of characters. Now, 2 to the 16th, we've memorized that. Maybe not yet. Is 65, 5, 36 possible characters. Now, when Unicode was first developed, somebody said the magic words of, well, we're never going to need more than 64,000 characters. Boy, were they wrong. Turns out that when people started looking around and they found things like they found the old American indigenous people languages, they'd find Navajo. There's a complete language which has characters unique to the language. They realized that in Korea, in Japan, in China, there are multiple languages, and many of them use a form that we wouldn't even be able to support using something like ASCII. And those characters all do exist. So currently, although not all of the positions are used, we're using 21 bits for Unicode characters, meaning that we can have that many characters, 2 million characters. However, we give up some of them because there's a range in which we have to do some funny business in order to support it. And the reason we might have to do some funny business is, remember, Java and all these guys are using UTF-8 or UTF-16. They can only go up to 65,536, which means, really, that is the biggest number they can support. Unfortunately, 21 bits looks like this. And it doesn't fit inside of 16 bits. Now, it turns out that really this number is a 0, but it doesn't matter because there's still 21 bits there that have to be dealt with. So Unicode, when used with programming languages using UTF-16, had to have some special attention because they, once again, did a short-sighted look at what they were going to be having to encode in the way of characters. So the modern ways of doing things give us something called UTF-32, UTF-16, and another standard called UTF-8. HTML5, the internet standards, use UTF-8. It's a somewhat compressed way of storing the characters, and it only gets big when we're not writing in English or in languages that tend to not use lots of characters. So it turns out to be a pretty good choice, but the standard requires a UTF-8 support by HTML5 programs. As I mentioned, UTF-16 takes 16 bits per character, and UTF-32 takes 32 bits per character. Now, here's the quandary we have with all of these. Let's assume that I didn't want to make things break that currently exist. That means I don't want to break encoding like ASCII. So what I'm going to do is I'm going to make sure that ASCII characters only take 7 bits. That means if I'm going to take the letter A, lowercase a, and I want to encode it, let me actually do it this way, as a 41. I have 8 bits here, 8, 8, 8. So what I could have represented in 1 byte in UTF-32 now takes 8 nibbles, which is 8 times 4, 32 bits. Now, if we think about the fact that ASCII is most of the web right now. Not always going to be, but right now it is. This is an extremely wasteful encoding. Although we don't have to do any funny business to put this number inside of it, right? That fits just fine. And also allows for a lot of growth. Using UTF-32 is often a problem. Now there's a secondary problem with UTF-32. Now you have to take my, well, I guess we'll probably do it in here. So I guess you don't have to take the other class to see it clearly. But there's two ways of encoding the bits anytime you're working on a machine. Machines have two architectures. One is called Big Indian, and the other is called Little Indian. Now, they don't have anything to do with indigenous people. What they have to do with a Gulliver's Travel story, where the people were in a big discussion, argument, fight, whatever you want to say, about which end of their egg they should stand the egg on, the big end or the little end. And so they were either on the big end side or the little end side. And that was taken, yeah, my story's not exactly correct either, but they were taken to mean describing how we're going to write numbers. Any number bigger than a byte, when written in big endian, will follow the natural ordering of the bytes. So this particular notation right here is UTF-32 big endian. I wrote it this way. This is UTF-32 little endian. Now UTF-16 only uses 16 bits to represent its data. So we know for a fact that we can fit our number in there. 0041 would be UTF-16 big endian. 4100 would be UTF-16 little endian. Now, if you received a file from somebody, you'd have to know which of these formats it's in. Very often, it's not always done, because sometimes it's simply done because you're supposed to know what it is in advance. But assuming you don't know what it is, they use something called a byte order mark, or a BOM. Byte order mark. And that will give you a clue as to what size and which ordering we're currently using for the ASCII character. Now, clearly, if the character we were going to encode, for example, 1, 2, 3, 4, that just fits fine inside a UTF-16 big endian. 0, well, it's a, whoop, did you all lose me there? This is UTF-16 big endian. It would be encoded as 3402 if we had it in UTF-16 little endian. Now let's assume for a second that the number I wanted to encode didn't fit in 16 bits. Let's just take a simple one here. Let's see. Let's say we take 1, 2, well, 1, 2, 3, 4, 5. That's what we could, and all of these numbers that I'm writing on the left here are called code points. It's going to be easy to encode in UTF-32 big endian. At UTF-32 big endian, which means little endian. I got something wrong there. 4, 5, 2, 3, 0, 1, 0, 0. So those are fairly straightforward. 16 is not. It won't fit. So we have to use something called surrogate pairs. What we're going to do is we're going to take this number, and instead of sending it as a single 16-bit number, we're going to put it into two 16-bit numbers and send it. Now, a naive approach might be, okay, well, what we'll do then is we'll take 0001 and we'll take 2345 and we'll send those. The problem is, that's a legitimate character. That's a legitimate character. We want both of these to be illegitimate unless they're taken together. So what we're going to do is we're going to have an algorithm which is basically going to generate us 10 bits of data from the left half of the 20 number and from the right half of a 20-bit number. And we're going to combine them with two numbers. One number is D800, which is called the high surrogate. The other is DCharlie00, which is called the low surrogate. So now we need to take an algorithm. Let me see if I can find my number there. And we want to figure out how we would go about doing this algorithm. Okay, the number right now has 17 bits in it. We can see that because each of these is a nibble, 4 bits wide. 4 of them would make 16. Plus we have the 1 bit of the next one, which is the rightmost bit turned on. So if I write this out in binary, 0001, 2, 3, 4, 5. So the numbers are significant up to this point. But what I don't have is I don't have enough bits here to break it into pairs 10 bits wide. So what I have to do first is I have to make sure that I have only 16 bits to work with. Okay, so to do that, before I encode it this way, what I'm going to do is I'm going to take my number, which is 1, and I'm going to subtract from it that number, which looks like 10,000, but it's not. It's 10000 in hexadecimal. Because we're not dealing with decimal system, we don't use the words. We specify each digit and just say the digit name. Occasionally we'll lapse into saying it wrong, but we shouldn't. So we're going to subtract that, which means the number I'm actually working with here is 02345, which is this number. Okay, now that we have this number, we need to make sure that we can combine it to make our two numbers that need to be added to the high surrogate and two numbers that would be, well, one number ultimately, but it works out to be two numbers, added to the low surrogate. So what we're going to have to do is we're going to have to take and split this number into parts that we can work with. So a reasonable thing to do will be to take 10 bits on the right, which is here, and break it apart. We now have 6 bits here. How many more bits do we need in order to make sure we have 10? We need 4 more. Okay, now I'm going to take the spaces out of these. And then I'm going to break it into sets of 4. Now, what I have here are 10-bit numbers that are going to be added to a 16-bit number. That means I really need some leading zeros. I need 6 of them. So I need those 4 plus the 2 to make that thing. I'm going to break this to a second line here. And he needs the same. He needs to have 4 zeros plus 2. It's this part that's going to be added to the high surrogate. And this part that's going to get added to the low surrogate. Okay, so here is our surrogate, D800. Again, this is why you have to memorize these things. D, why does that always happen? D800. And this guy is going to be a DC00. So just kind of looking at it intuitively, we haven't done arithmetic yet, but you can see that anything that's 2 zeros will stay a 0. Anything where you have a 1 and a 0, a 1 will come out. We don't have any place where 2 1s line up, so it's no carries. So this is going to be 1101, 1000, 0000, 1000. This guy, 1101, 1111, 0100, 0101. So if we read this number out, this guy is equal to B808, and this guy is equal to BF45. If I take those two numbers, D808, BF45, I just wrote out the UTF-16 big indent encoding of that. Now, because we're working with 2-byte entities, when we make it little indent, it's only the little indent parts that get changed. I think everything can get on the screen there. Do you have a question, Mikhail?
Yeah, you hear me, right?
Say again?
Can you hear me?
Yes, I can.
Okay, so which zeros are we turning into ones?
You mean when you do the addition?
Yeah, like you said.
Well, we do the addition. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 0 is 0. We're just simply doing simple arithmetic with 1s and 0s.
Okay, yeah, but wait, how did
This number is the extracted number that we got when we broke this into two 10-bit parts and basically added 6 zeros in front of each half.
Mm-hmm. Yeah,
Okay, we're going to go over another one of these. Don't get too caught up on trying to, learn it the very first time you say it. Okay, now let's do another one of these because I know they can be a little problematic. Let's take this number right here, 12338. We didn't know what that character was. We could take the code point, go to the website, go to unicode.org, put in the code point, hit go. It'll give you all the times it's been changed, but right now it's currently inside this PDF. You can open the PDF. You'll see that we're writing a character from cuneiform, and the actual character we're writing, 12338, I believe is what we had. One, 2, 3, 3, 8 is this character right here. Now, if we were on an exam or something where we had the 1, 2, 3, 3, 8, in the back of the same page you're on, if it asks you what does code point, what's the name of code point 12338, you'd look it up in this table, and that's what you'd cut and paste into your exam as being the name of that particular character. And then again, if you search one more time, you'll find the character again in the table, which is right here. So let's try to translate that guy, following our stepwise procedure. First thing we do is we normalize the number by taking away what looks like 10,000. That leaves us with 2338. Write that out in binary. 2, 3, 3, 8. Now we need 20 bits in this number, of which 10 come from the right-hand half, and then the rest are this piece here, plus any leading zeros that we haven't written down yet. So here's 4, 4 plus 2. So the second number we're going to be using is that guy. First number is this guy, but he's already 4 zeros too small. And of course, he's not grouped correctly for nibbles. So let's go ahead and fix that. All we did is change the spacing. Now there's 10 bits. There's 10 bits. We have to turn them both into 16 bits. So that means we have to add some leading zeros. We need 6 on each of them. We need 4 of them, and then 2. We need 4 of them, and then 2. Now we take the top number and we add D, 8, 0, 0 to it. And in the bottom we add a D, Charlie, 0, 0. We should be able to just add those up. 1, 1, 0, 1, 1, 0, whoops. And down here, so this number here is our high surrogate. And he is D808. Right here is our low surrogate. He's DF38. Our answer, if somebody asks us what the UTF-16 big end is, it's D808, DF38. If they ask us for UTF-16 little end, it would be 08, D8, 38 DF. So I would suggest you find some other people in the class to practice with, obviously, on these. Just don't forget the first step, where we have to remove this to get us down to 16 bits. Now you might say, what would happen if I had this number, the biggest number? Well, when I subtract that from it, I'm going to wind up with this. We haven't done the math yet to see why that's the case. But notice this has 4 bits that are above the 16 we needed. But that's okay. It just means when we do our addition over here, we're going to have some things combined with these bits as well as the ones that were combined over here. So it can handle everything. And this little hole we have here is because of the fact we've eaten up all the values that are in the range from D800 up to DF00, which is where all the high and low surrogates live. And because of that little shuffle with the subtracting the 10000, they actually are the numbers that would fill in this hole here. Now, we'll need to be able to do these in both directions. I'm not going to go backwards on these right now. I'm going to just let you learn how to do them in the forward direction, because all of this becomes immensely easier once you've memorized your powers of 2 and your nibble values, being able to convert in and out of binary into hex and those. And additionally, there's some arithmetic we have to do that I haven't taught you any of the rules for binary arithmetic yet, other than just saying 0 plus 1 is a 1, which makes sense. But 1 plus 1 is a 2, and obviously we don't have that digit. So we'll have to do some business in class next time to make sure that we know how that works. Okay, there's still one other form of the Unicode that we haven't talked about yet. UTF-8. This is the code of the web. Now, it takes advantage of the fact that ASCII sits in that bottom 7 bits. UTF-16 requires us to use 16 bits for every ASCII character. UTF-8 requires us to use only 8 bits for every ASCII character. It uses a compression scheme. Now let's talk about how that might work. First of all, any number or any value character in UTF-8 that begins with a binary 0 is ASCII. So there are 7 bits available for ASCII characters, which can just be encoded with their exact values right into that. But that also means no other character in UTF-8 can begin with a 0. What they do begin with is the number of ones that are going to be the number of bits that are going to be available by taking 2 bytes of data. So 1-1 says, I'm going to give up 2 bytes of data. This is one of them. And the next one will always look like this. So I'm missing 1 0 here, I'm sorry. The 0. And the next one will look like this. And it'll always have 6 bits available. So that pair has a total of 11 bits available. So any Unicode character that you can encode in 11 bits or less, but not 7 or less, can be encoded in these 2 bytes. What if it's bigger than 11? Well, if it were 3 units long, we get 4 bits here. And then I have two of these. Giving me a grand total of 12 plus 4, or 16 bits. Now notice that 16 bits here is spread out across 3 bytes. So UTF-16 is a better code if you are having characters that are 16 bits. Because here it would cost you 3 bytes. There it only costs you 2. However, ASCII only costs you 1, and since it's most of the web, you know, all the HTML tags and everything there are all in English, then the ASCII values, the 7 bits, will be much smaller. Well, I still haven't gotten 21 bits. What's going to happen if we do another one of these? Where we say 1111, we'll get 3 bits here. Six bits here. Spelled that wrong every single time. And of course, it says I'm going to have 4 bytes. So 1, 2, 3, 4. 6 is 18, 19, 20, 21. That's handy. So in 4 bytes, I can encode the biggest possible character in Unicode. So let's do a UTF translation. Let's say that the code I wanted to do was lowercase b, relative to 6, second character. It looks like 0110, 0010. That's the binary for it. How many characters did we actually use? Well, starting at the right, 1, 2, 3, 4, 5, 6. The last one is in the 7th position, so it'll fit in this. So I would encode it exactly like it's encoded. So the UTF-8 is 01100010, which is again a 62 in hex. Notice it's identical. Notice also, because it's 8-bit long, there is no such thing as big endian or little endian. That only applies to multiple bytes. So let's say we wanted to take the number 1, 2, 3, 4 and encode that. That's hex. 1, 2, 3, 4. Oh, we have 4, 8, 12. It's 13 bits long. Won't fit in here, so it's going to have to go in this. So we're going to have a 1110 XXXX 10 112 2 3 4 102 1 2 3 4. So the basic guy is this. Now we have to take this number and fill it into all the holes here. So starting at the right, that'll be underneath that. Those two will be there. I have no idea what I'm erasing right now. My keys aren't working. There they go. So this is only 2 of these. So these 2 zeros here really are over here. I'm going to do this differently because my keypad has not got a 0 working right now. I have to type 4 digits out of this, which are going to be 0100. The 1 here goes right there. This is going to be 1000. Next one is just 2, so it's a 00. And then we have those. We'll go right here. Okay, so let's combine the numbers together. And this guy's going to be 11100001, 1000, 1000, 1011, 0100. We can write those out in hex. It's E188. B4. So this is the UTF-8 for the value 1234 in hex. Let's actually go look and see if 1234 is really a character. Sometimes they are, sometimes they're not. We go here, we put in 1234, hit go. There's a page. Ethiopic 1234. Let me find it. It makes it easier to spot. Its name is the Ethiopic syllable C, and it is on this page 1234, which is right here. So it's this character right here. How about them apples? That's pretty good, isn't it? Okay. Are there any quick questions about Unicode conversions? Robert?
So then if any UTF-8 starts with a 1, that means it's going to be multiple bytes or multiple bytes.
If it's more than 16 characters, oh, I'm sorry, not more than 16. If it, where's that table again? If you have 7 bits or less, you're going to fit into 1 byte. If you have 11 bits or less, you know, obviously you could put 7 bits in here, but you wouldn't. It fits into 2 bytes. If you have 16 bits or less, it'll fit into 3 bytes, and all the rest of the characters will fit into 4 bytes. So it doesn't matter what the numbers are. If I gave you a number that looked like this, and you wrote out 0, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 characters. Okay, if we have 14 characters, it's bigger than 11, it's smaller than 16, so it's going to require 3 bytes to write that number out. Again, that'll make good discussion for you and some other student in the class to come up with how you would even work this problem. What if you were given this and had to go backwards? Any other brief questions? Encoding is very important. Many of the things we do, we have to remember what we're putting in those bits ultimately may just be electrical signals. And if we have a positive signal versus a ground signal, and we don't know which is which or even what it means, then there's no sense in writing, code to work with it because the context of the information has been lost. In the case here where we're simply working with alphabetic characters, that's such a common use case. And since both the web and languages like Java and C# and the modern languages have moved into using Unicode, just like when I was, doing my studying and things, ASCII would have been, well, actually there was a different language at the time I started, but those would have been very critical that you be able to tell those, because you can't tell from just looking. If I give you an 8-bit number and I ask you, what does that mean? That's a tough question. One of the things we can tell is it's not ASCII unless it's ASCII with parity. If it's ASCII with parity, how many ones do we have? We have 1, 2, 3, 4, 5, 6. It would have to be even parity, or it has an error, or it could be mark parity, or it could be one of those no parities, but we're rarely even talk about those. But the problem is, I don't know if that's supposed to stand for 11 times 16 plus 11, or if it's supposed to stand for some alphabetic character. The number it would stand for, the letter it would stand for, is if we assume that to be a parity bit, what's left is a 3B. Now, what do we know about 3B in the numbers? Well, we memorized 30 to be the start of the numbers, or 3Z. It's what a 0 is. So it would be the 11th number. Since there isn't an 11th number, we'd have to go look at the chart. Look up 3B. We find out it's a semicolon. If it were an ASCII character. But what if it's not an ASCII character? What if what we're trying to represent here is 11 times 16 plus 11, meaning that there was no parity bit. This bit is actually real data. Well, we could calculate that. And where'd my calculator go? Did I close it or lose it? I probably lost it. Yeah, I lost it. I'm not going to bother getting it. But 11 times 16, what's that, 171 or something, plus 16? Well, we don't know which it is. So we have to learn these encodings so that if somebody gives us context, we're able to understand what those bits really do mean. So from the first part of our assignment tonight, we need to memorize the powers of 2 from 2 to the 0 up to 2 to the 16th. We need to memorize our nibble table, 0, 0, 0, 0 up to 1, 1, 1, 1, both in hex, binary, and decimal, so we can move among any of the three there, because you see we're needing them all the time. And we need to memorize from those anchor points where the numbers are in ASCII, where the lowercase letters, the uppercase letters, where the space is, and where carriage return and line feed are, because they're the end of line characters. And that'll be easy. I mean, you just take some time and just do it and it'll be done. And then you never forget it. Okay. So let's talk a little bit about Ohm's law. I will need my whiteboard, which is probably down here somewhere by this point. Now what I'm going to do is we're going to take kind of a circuits approach to learning about these. If we were in class together and we had hands-on together, after we learned about these, we'd actually sit down and build some of the circuits. But unfortunately, we're all coded into our own areas for now. So hopefully, in the future, some year or two from now, when we're all doing this class in person, you can come back and you can do some of these labs with us. First of all, I'm going to draw what's the equivalent. Let me do it in black here, actually. I'm going to draw the equivalent of a battery. We're drawing a schematic diagram. This is the way a battery is indicated. There's actually some formal meaning about the long and short lines and how many there should be. I'm going to always draw it this way. The plus or positive end of the battery is the long line. The minus end is the short line. In a circuit, this will normally be labeled as a part with the letter V for volts, or in our case, voltage source, and the quantity of voltage inside of it, meaning the pressure it's exerting on the circuit, voltage is really a pressure, will be measured in units of volts, V-O-L-T-S. Now, this is wire. I'm going to take the top of the battery and hook it to the bottom of the battery. Now, in real life, this behaves slightly differently than I'm going to describe, but in the picture here, what I've done is I've created what's called a true short circuit. Voltage is pushing electrons basically out of the battery and around the wire that connects it back to the other end and then re-receiving the electrons. Well, if we did this directly connected, every point on this wire is assumed to get rid of no voltage, meaning the pressure remains constant. Because of that, we would have a short circuit. And basically what would happen is we would burn up the circuit. To prevent that, we're going to add to the circuit another element, which is called a resistor. Looks like a little ziggity line. It'd be labeled in the circuit with an R, and it's measured in units of ohms, which are using the Greek omega to indicate the value of them. If you think of this as being the pressure behind a hose, this is basically the diameter of the hose. How much, even though you're pushing, are you going to actually get through? Because you can only get through so much, assuming you're pushing was sufficient to fill the hose. So we've got a pressure pushing current through the circuit. Now, the engineers actually know better, but they go back to early electronics and electricity development, and they cause current to actually flow the wrong way through a circuit. Instead of electrons coming out the negative end and going to the positive, they've invented something they call conventional current. And we're going to use it also because that makes us consistent with all the literature and with the way engineers think. So conventional current, which will be labeled in the circuit with the letter I, and is measured in amperes, letter A, or we'll call them, for our purposes, just amps, AMPS, is the actual flow that's going on through this resistor. And it turns out there's a relationship, and the relationship is called Ohm's law. Ohm's law says that the voltage that a particular device is dropping or is using is equal to the current passing through that device times the resistance of that device. So let's assume for a second over here, we have 10 volts. And we have a resistor over here of 10 ohms. Because V is equal to IR, we simply take the volts, bring the R to the other side, divide it into it. 10 volts divided by 10 ohms means we have 1 ampere of current flowing in the circuit. One of the things you can do, you can draw a circle, split the bottom, put a V here, put an I here, an R there, and then cover up the one you want. If I want voltage, I'm going to cover it up. Notice the I and the R are next to each other, so I multiply I times R. If I want to find the current, I divide the voltage by the resistance. If I want to find the resistance, cover it up, I divide the voltage by the current. And all those relationships work out with each other for any circuit we're using. Now, we're talking about direct current or DC circuits here, and we won't need to, in this course, talk about alternating current circuits. There's slightly different rules. The spirit of them is the same, but we have some other devices which behave slightly differently, and they actually don't produce real power, and so that causes it to appear to be working differently. Now, although it doesn't have a formal name, we often call it the power law, is another law that we need to know about. It says that the power in watts used up by a component is equal to the current through the component times the voltage dropped by the current, by that component. So we could draw another one of these if we wanted. An I here, the V there. Cover up the one who, however, power is in watts, W-A-T-T-S, watts. So in our case, we had 10 volts of pressure on our device, and the device had 1 amp going through it. So 1 times 10 means we were dispersing 10 watts worth of power. And the resistor has to be made accordingly. This is going to get rid of this wattage, in the case of resistor, by way of heat. The heat is going to be quite high at 10 watts. Most of the resistors we use in electronic circuits are going to be in the range of 1/8 watt, 1/4 watt, 1/2 watt, much smaller values. Now, we also, in a circuit, might have multiple components. Put a resistor here, and a resistor here, and come back again. I'm going to use, for our voltage supply here, I'm going to use 10 volts. For my first resistor, I'm going to say it's 100 ohms. And the second resistor here is going to be the same thing, 100 ohms. Now, a reasonable question to ask would be, if I'm going to the store to buy one of those resistors, what size in watts should I be buying? Okay, well, let's calculate the problem. Well, the voltage is pushing at a pressure of 10 volts. It's passing through both resistors. Now, in all of the loops like this, there's a law called Kirchhoff, we'll put a KVL here, Kirchhoff's voltage law. And we'll look up Kirchhoff later. It's Kirchhoff, I think. I can't spell it without writing it. This is too hard to write with. But Kirchhoff's voltage law says the sum of the rises is equal to the sum of the drops as you go around a circuit or a loop. So if this goes up 10 volts, it's got to come back down 10 volts by the time we get here. Now, volts are always measured relative to a reference point. I'm going to draw mine like this, a little ground indicator, meaning that relative to this spot, this is equal to 0 volts. Here is equal to 10 volts. Since the wire in between doesn't drop anything, here is also equal to 10 volts. In here, we don't know. But we know by the time we get here, because it's connected to that, we're back to 0 volts. So we don't know the current. And we're trying to figure out basically what is the voltage at this spot so we can determine what the voltage drop is across this resistor and determine what the wattage is so we can pick out the right size resistor. Okay, a reasonable thought. These are the same size. Maybe it's 5 volts when we get there. It was 10 volts here, 5 volts there, 0 volts here, because it dropped an equal amount across each of the resistors. And if I think about it, if the current doesn't change and the resistor is the same, Ohm's law says that that current times that resistance has to equal the voltage. Since both of those would be the same and they both have to add up to 10 volts, our guess that this is 5 volts is a completely reasonable guess. So, how much current is actually going through this circuit? Well, that's going to be a little harder to figure out for us, but not necessarily. If this was 10 volts here, and this is 5 volts here, how much voltage dropped across that resistor? We know 5 volts drops here because it goes from 5 to 0. We go from 10 to 5. How many volts do you think that is? Give me a green circle if you think it's 10 volts. Give me a red circle if you think it's not. Okay, give me a green circle if you think it's 7 volts. Or 10 and 5 makes 15. Give me a green circle if you think it's 15. How many people think it's 5 volts? Okay, well, 5 volts the answer. To go from 10 to 5 is 5. So the drop across this, the pressure change across this is 5 volts worth. So V equals IR. So if I take the 5 and divide it by 100, and I'm not going to try to do that, even though I could probably do it. I'm just going to use the calculator. Five divided by 100 is equal to 0.05, 0.05 amps. So that's what I is equal to. So that times the 10 volts will give us the power. So this number times 10 is equal to 0.5. Watts. Which is clearly a half a watt. And remember I said that's one of the common uses we have? Now, we normally would not buy a half watt resistor. Normally we will buy, if we're right on something, the next biggest one. We want to allow as much cooling as possible rather than running it right at its fringe thing, because the half watt's an estimate. It may not be exactly right. If we give it a little more than a half watt and it's really rated for less, we could burn it up. So the one we're going to go get is a 1 watt resistor. Now, the other thing is that if we presented this answer we're going to use a different way of doing things in here. Basically, we're going to use what are called prefixes. The prefix says, and we have that on our web page, that we're going to use terms like this. The unit is right in between M and K. For the number of positions we have to move the decimal point in order to put our number into a standard engineering format. So let's look at how we would go about doing that here. First of all, for almost all the problems we do, we're going to use 2 significant digits. Two of them. Not 3, not 4, not 1, but 2. So in our number right here, we rewrite it out. We have a 5, which is significant. We need the 0 that follows. So both of these numbers now become significant. Leading zeros are never significant, at least in what we're doing. Now, moving it 3 points at a time, I want to move the decimal point so that I have either 1, 2, or 3 significant digits to the left of it. So I'm going to move it 1 set of 3. Now I have 3 to the left, but I have 2 significant digits, so that's okay. It needs to be either 1, 2, or 3 significant digits. So my answer is going to be 50 times 10 to the minus third, which is milli. So the way I would present this answer is 50 milliamps. The same thing with this watt answer I got. If I was asked what that was, first of all, I would see it's 0.5. I have 1 significant digit. I need to add a second one. Now I need to move this 3 positions to the right in order to get, if I might have to move to the left, but in this case to the right. So 3 positions, it would be to here, meaning I had to add another 0. Now I look and I make sure that 1, 2, or 3 of these are significant. Well, 2 of them are, so I'm done. So the answer here is 500 milliwatt. So we go to the store, we go to Radio Shack, they have a few stores still open, and we say we need a 100 ohm resistor, 1 watt in size. He goes and gets it for us. We look at it. How do we know from looking at it that it's a 1 watt resistor? Anybody want to take a shot at that? Throw your hand up if you want to. Peter?
In my experience, resistors have different colored stripes based on their size.
Okay, that's close. That's where we're going to get the value from. Unfortunately, the answer to the thing is, once you take it out of the package, you better remember what it is. Only the packaging tells you what the wattage is of the resistor until it gets fairly big. If you get a 1 watt, actually might be marked on the resistor, but chances are you have to get bigger than that before you start to see it. However, as he pointed out, the value, the 100 ohms, we can check. On the website, I love this website. Oops, where'd it go? I've lost my website. We have a thing called resistor colored codes. Now down at the bottom, you'll see that there are 2 bands which indicate our 2 significant digits. Then there's something called the multiplier. And then there may or may not be a tolerance band. So to read this, if we wanted 100 ohms, the first band would need to be a 1. A 1 is brown. The second was a 0 of our significant digit. Remember, we had a 1 and a 0. That was our two significant digits. It's a black because it's a 0. The next one says, now after your significant digits, how many zeros do you want to add? Well, to get 100, we want to add 1 0. So we need to add a brown band for that. So we have brown, black, brown. Then finally, sitting a little ways away from the other band, there may be either no band, meaning this resistor could have a value 20% high or 20% low, meaning it could be as low as 80 ohms, as high as 120 ohms. Or if we have a silver band, it could be 10% high, meaning it could be 110 or it could be 90 ohms. Or a gold band, meaning it could be 105 or 95. And there's other colors, but these are the ones you would encounter. So those are the way you would read a resistor. So a reasonable question would be to you, if somebody gave you a red, orange resistor color code, what would be the value of it?
Is it 7?
Let me grab my white thing here. Okay, so we said red, orange. Red is a 2. Red is a 2. There's our two significant digits. Now we need to add 3 zeros. So our decimal point's right there. If we go 3 positions to the left, none of our significant digits fall in that range. So in order to say the name of this resistor, we have to move the decimal point from there to here. This is in a positive direction. So we have 22. 10 to the third is a K ohm resistor. And because it has no fourth band, it may be 20% higher than that or 20% lower than that in terms of its actual resistance. What wattage is it? We don't know. We have to look at the package. So let's take another number here and try to work with it for a second. Let's say that I had a brown green, red, gold. See if you can figure out what the value is and how would we say it. Put your hand up if you know. I may or may not call on you. I just want to see who knows. Now, come on, guys. This is easy. This is like matching the colors. Okay, well, quite a few of you are getting it now. Brown is a 1. Green is a 5. Red says there's 2 zeros. Puts our decimal point right there. If you go to the left, we haven't captured all of the values, so we can move it 1 position over. Now, is there 1, 2, or 3 in this set and nothing beyond it? Absolutely. So we have 1.5. We moved it 3 in a positive direction. K ohms. Gold says 5%. So it's plus or minus 5% from that value. Now we very carefully designed our circuit. And we came out with the fact that we need a 482.3 ohm value. What value are we going to go to the store and ask for?
Is it going to be 4.8K?
Hold on, wait until we call on you because somebody else might have an answer also. Okay, Scott, what was your answer again?
In real life, I'm thinking a 500 ohm resistor.
We need 2 significant digits. We need 4 and 8. So this is not significant here. That's not significant there. So we can strike that, but the decimal point didn't move. So we would think a 480 ohm resistor. We would also calculate whether we needed plus 5%, 10%, 20%, and the wattage. Problem, of course, is the problem he alluded to when he was just speaking, is when we go back to the store, there are only certain values available. Now, if we had picked a 10% value, we'd find the closest we can get is 470 ohms. So we probably would do that. We'd redo our calculations based on 470 ohms to make sure everything was still safe. If it turned out things were getting too hot, we might go as far as 56, but that's fairly far away. If we're going at 5% values, we have a little bit of a difference here. 4.7 is really close to the 480, and these other two are getting further apart. So again, 470 is kind of the one we would vote for if we were going to buy it. Now 470 we can actually do the color codes on. .470, yellow, violet, 10 is brown, and it's going to be either 10% or 5%, so it's going to have either a silver or a gold. Now, it's really easy to memorize these. It's not imperative that you memorize them, but it'll certainly make your work faster if you do. And they're just basically Roy G. Biv in here. If you take a look at the ordering, and you start to figure out what they are. And then this stuff just kind of sticks in your head once you've done them a couple times. Remember, we're using our bands, 2 values, which are significant, and then the multiplier, don't forget about this. It's the number of zeros we're going to add after the 2 significant digits. We always want to move our decimal point so that there is either 1, 2, or 3 significant digits to the left of it, and then beyond that next set of 3, there are no more. And then we use the prefixes table to figure out what we need to do. Okay, what is today? Today is Wednesday? I mean,
Yeah,
I'm pretty sure. So we will be getting back together again on Monday night. Be on time. You can look at the syllabus to see the sorts of things we'll be going over. Plan on me calling you by name, whether you got your hand up or not, to answer some questions for me next time. And, you know, this class takes a lot of work. You'll plateau now and then. Sometimes you'll think, my gosh, what's he talking about? He's making it really confusing. When you get with other students and you study it, you read about it, you talk about it, you go, oh, that actually is kind of easy. This is not a lecture class. We're going to learn how to do this stuff through the way of me presenting it to you, and then you using what we have done to answer questions about it. So we're very likely to do some circuit questions with multiple resistors. There's some other rules about multiple resistors I haven't told you yet, but you very well may derive them in thinking about the problems we did. Anybody have any last minute questions other than reteach the class again type of things? I apologize if I don't remember some of you, by the way. I think some of you may have been in the class before, but I won't remember you because I get about 100 people a semester. And it's just too hard to remember all the names. So if you've had me before, welcome back. If you haven't, you know, then good luck. Mikhail, you have a question?
Did you take attendance?
I have already taken attendance. The machine does it for me. But thank you for asking. Okay, then we're done for tonight. Say goodbye to me. Turn your mic on and just say goodbye, and then I will see you Monday night at 6.
Good night.
Goodbye.
Bye-bye.
Night.
Bye-bye.
Thank you.
Bye-bye. Bye-bye.
Have a good night.
Good night, Professor.
Good night.
Goodbye, Professor.
Bye-bye. It's already inside. Now I put it in front of the door. Well, not in front of the door, but like next to the door, next to the food, dog food. So now you come to my room. Mr. Thor, he heard your voice and he ran here. He's jumping on me now. There's another Peter in my class, and now it's very confusing when the teacher calls on like one of us. I'm not sure who he's calling out to. No, I don't think I will. I can go by Pera.
Get an equation.